Hello, welcome back to Math with Patrick. Today is June 2nd, and we're solving problem number 153 from the Daily Epsilon calendar. And we just got to show why the answer is 2 today. So we need to find the ratio of the area of these two squares. All right, so we can, assume that these are squares because it tells us they are. So there's some 90-degree angles. All of these are going to be the same length. And then we're going to have some 90-degree angles here in these corners, and then all of these are going to be the same length. And I think the interesting part here is that the diagonal of the small square is the side of the large square. And I think, how about let's kind of name these things. So I'm going to name them square 1 and square 2. And so S1 is going to be the side length of the first square, the small one. And so the area of the first square is just going to be S1 squared. So likewise, on this other square, I'll have S2, which is just the side length of the larger square. And then the area of the larger square is going to be that side length squared. And then that kind of interesting relationship is that the diagonal of the first one, so I'll say D1 is the diagonal of the first square, is going to be equal to S2. So I'll say D1 equals S2. And this right here, it just means the diagonal of the first square. And how about let's just assign some numbers to this? I don't think it would hurt to just say that S1 is equal to, let's just do 1. That seems like an easy number to pick. And so if we decide that S1 has a length of 1, then the area of the first square, A1, is just going to be 1 also, because it's just 1 times 1. Now, from this, we could figure out what D1, that diagonal, is. We could just do a little bit of a Pythagorean theorem here. If we have a right triangle and 2 of the sides are 1s, then we can do 1 squared plus 1 squared equals c squared, c being the hypotenuse. And so simplifying, we get that the hypotenuse is equal to root 2. And so that's going to be this length right here. And so since the diagonal is root 2, that means the side of the second square is also root 2. So I can kind of decide that S2 is going to be equal to root 2. So when I plug in root 2 here and I square it, I'll get that the area of the other square is 2. And then here, at least in this one example, I can show that the ratio between the two squares is 2. Though maybe you're thinking, okay, well, is this a special example? Is it special that this was a 1? So what I can do to generalize it, I could just put an A right here, where A could be any number. And so when I plug in 1A, actually, let's just do that. Let's just plug in A here. That would be an A there. And then when I square it, I'll get the whatever A squared is. And then doing this Pythagorean theorem, I would get A squared plus A squared, which is 2A squared. And then simplifying this, 2A squared. And then simplifying this by taking the square root of both sides, I get root 2 times A as that diagonal, as the hypotenuse. And so I can replace this, root 2, with a root 2 times A, and then plugging in that general value into the area of the second square, I will get 2A squared back. So it doesn't really matter what size the original square is. I'm going to always get this relationship where if I take the small area and I multiply it by 2, I'm going to get the bigger area. And so the ratio of the area of the squares is either 1 to 2 or 1/2 if you're thinking big to small, or the ratio is 2 to 1 if you're kind of thinking small to big. And 2 is today's date, and that's kind of where our answer is coming from, just because we got to double the smaller area to get the larger one. All right, that's my explanation. I think we're all done. I'll catch you tomorrow. Alrighty, bye-bye.